The internet is a vast plain of immeasurable knowledge and robust connectivity. There are many varying reasons why someone may want to access the internet, but for the most part, it's used for the aforementioned qualities. However, there is an undeniable presence of content wherein productivity and research are simply an afterthought of use. Nevertheless, I find myself in both instances of usage. Yet, there are times when mindless scrolling and curious intuition intersect. On the video streaming platform YouTube, there's a video of a man jumping from the side of a house into a pool. However, after performing a flip in the air, he finds himself slamming his head onto the edge of the pool at a fast speed. The sound alone from the video is enough to drive chills for anyone within earshot, me included. But morbid curiosity struck upon watching this video a few times. How badly was this man hurt in the video? After this question, I instantly went to work in using classical mechanics to ascertain just how hard this man hit his head on the edge of the pool. Here, we will use various different physics concepts and apply them in order to determine the potential injuries the man in the video sustained from his pool dive failure. Now, before we can crunch numbers and dive right into the problem, we need to examine the video in order to get an accurate sense of scale. There aren't any clear objects with an easy sense of scale on the same depth as to where the man is standing/falling. Top it all off, there's never any point in the video where our subject stands straight up. Luckily, there is a small window just above our subject towards the beginning of the video. Assuming that the window complies with standard window sizes, it's likely that the window itself is 36 inches tall, meaning that we can use this in order to determine our subject's height as 6 feet or 1.6 meters. And this is when estimating roughly how tall he would be if he were standing straight up. From there, we can measure the wall to be around 2.9 meters tall. This problem is also going to deal heavily with the subject's center of mass too, and this center of mass, when watching the video, appears to be right around the subject's waistband region. By using head to body and torso to leg ratios, we can then determine the subject's center of mass to be roughly 3.7 meters from the ground, or in this instance, the pool water. Lastly, we can use a prediction of our subject's body mass index in order to deduce that he likely weighs around 70 kilograms. One may think that the next logical step is to gather the length of the pool, but this actually isn't necessary with the type of problem we are dealing with. Why is this? You see, the center of mass of our subject follows a parabolic pathway from the roof to the edge of the pool. The vertex of this parabola, the very highest point, never exceeds its initial starting point, meaning that this is not a projectile motion problem. It also isn't necessary to use trigonometry to find the hypotenuse of the triangle in order to calculate displacement, nor is it necessary to use quadratics in mapping out the parabola of the path the center of mass takes. This is because Newton's first law of gravity, which states, among other things, that objects falling from the same height will hit the ground at the same time regardless of horizontal velocity, so long as there is no upward velocity to counteract the force of gravity. If you hold a bullet in one hand and a loaded handgun pointed straight out in front of you in the other, shooting the gun and dropping the bullet from your hand at the same time will result in both bullets hitting the ground at the same time, so long as the ground is level in the direction you shot the gun. In this problem, we see that there is no upward force pushing the subject's center of mass past the vertex. Therefore, we won't need to take any measurements other than the height of our subject, the height of the center mass from the ground, the height of the building, and the weight of our subject. Since we are going to be dealing with vector quantities with directional information, we need to establish that the velocity moving down towards the ground will be considered positive, and angular rotation will be considered positive when moving clockwise instead of the traditional counterclockwise. So we're going to start this by drawing our subject at the top of the ledge right here. We're going to bring the wall down and draw little ripples on the ground to represent the pool water before cutting off the ledge where our subject hit his head. Next, we're going to include the height of the building and the height of the center mass right there. If you haven't gathered already at this point, the center of mass for our subject is right about where the legs and torso meets, as I mentioned earlier. This is the center of mass because this is the only part of our subject's body that consistently follows a parabolic path, and we will need to hone in on this spot in particular if we want to get the linear velocity of the object as a whole. Don't worry, this will hopefully make sense in a little bit later if you're lost right now. Anyways, we have our time that gravity acts on the subject as zero point 0.6 seconds, and the distance from center of mass to the ground as 3.7 meters, giving us a downward center mass velocity of 6.2 meters per second. That's the speed in which our subject's center of mass lands in the water just before the ledge that his head makes contact with. Okay, great. Now we've got that figured out, but it doesn't tell us much. According to Newton's laws of rotation, the outside of a rotating object will always spin faster than towards the center of the object. Look at the subject as he spins. Notice how the entirety of his rotation can fit somewhat consistently within a static circle. We can actually use this to our advantage in calculating our subject's angular velocity. But what exactly is angular velocity? Angular velocity is the speed in which the outer bodies of a rotating object move, and it is expressed by the equation angular velocity equals angular rotation over time. The theta symbol represents the angular rotation, and the W here represents our angular rotation. Now, we can choose the point where our subject is upright in the air to when he slams his head into the edge of the pool, and this is about 1/4 the circumference of our circle. That means that the total radians of our angular rotation will be 1/4 2 pi radians, since a full circle is just 2 pi radians. All right, now we can analyze the footage once again to discover that the rotation took about 0.3 seconds to transpire, so we plug in our values to get 5.2 radians per second. Now, obviously, looking at this velocity product, we can't use this quite yet. Why? Well, this needs to be converted into linear velocity, and we can do this quite easily actually by taking the radius of the circle, which I estimated to be about 0.6 meters, and multiplying it by our angular velocity to get 3.1 meters per second. Now, once we're done with that, we can take our center of mass velocity of 6.2 meters per second and simply add 3.1 meters per second to get an overall velocity of 9.3 meters per second. And we're able to add these velocities together because our subject is perfectly perpendicular to the ground upon impact. With this, we can then move on to calculating the amount of kinetic energy endured during the impact. We can do this by using the equation E sub k equals 1/2 times mass times velocity squared. Once we plug in these numbers, we get a result of 3,000 joules of energy, or 3 kilojoules. What does 3,000 joules to the face feel like? Well, Mike Tyson, a former professional boxer known for his absolute brutality in the ring, punches at about 1,600 joules. So imagine getting punched in the face by Mike Tyson twice at once, and you'd be getting about 200 joules more energy than what our subject endured here. What instantly grabbed my attention, though, was the phenomenon of whiplash. You see, whiplash most commonly occurs in car accidents, but it can occur in pretty much any scenario which enables it. This is when the neck is suddenly plunged forwards or backwards at high speeds. Symptoms of whiplash include dizziness, tingling or numbing sensations, extreme headaches, stiffening and swelling of the neck, and other painful and uncomfortable symptoms. Whiplash can occur in car collisions as low as 10 to 15 miles per hour, but if you look back at the velocity of our subject and convert it, you'll find that his head is speeding towards the ledge at a little over 20 miles per hour. It's also very likely that this impact caused unconsciousness in our subject. One key indication of this is at the end of the video, we don't hear water splashing, which would indicate that our host likely fell unconscious while in the water. This isn't good, suffice to say. Falling unconscious while underwater can cause either immediate drowning or dry drowning later on land. So overall, it's my prediction that it's highly likely that our subject either died or was seriously injured during the act of this stunt, which is why I'm not going to show the actual impact. You'll have to find that video on your own. That pretty much sums it up, what I have to say about this problem. So I hope you learned something, and I hope you enjoyed the video.